Uh, Welcome to Gadolin's Science Thursday. I'm Dr. Anže Zupanc, and today I will be telling you something about recycling of noble metals in alternative media. So I did my PhD in green organic chemistry at Faculty of Chemistry and Chemical Technology in University of Ljubljana in Slovenia under the mentorship of Professor Marian Jereb. And then I went for my postdoc here at the University of Helsinki, where I'm currently working as a member of a research group from Professor Timo Repo called Catalysis and Green Chemistry. I'm working with the recycling of noble metals among other metals, so today I will be telling you something about our research using alternative approaches to this severe problem. So noble metals are scarce in Earth's crust. We have limited amount of them, and sooner or later we will have to start recycling them from the waste sources, so-called secondary sources, to kind of accompany the extraction from the minerals. So recycling is necessary and will become more and more compulsory in the future. But recycling is not only necessary, it is also an economical opportunity, since the content of the metals in the secondary materials, so in waste, is, for example, can be 10 times higher than in average ore. Therefore, it's necessary and it's economical. And of course, we want to design the procedures that are sustainable, using sustainable materials to extract these metals, and that are selective. Selectivity somehow, as I will show you later, translates into the sustainability, because if we have a selective procedure and we take metals out of the waste materials one by one, we can also reduce the number of processing steps in this procedure and therefore reduce cost and time and materials that we use here. So typical waste substrates that are rich in noble metals are, for example, waste computer and cell phone components that contain copper and gold, automotive catalysts with platinum group metals, solar panels that have a large quantity of silver, batteries, for example, based on silver and cobalt, fuel cells made of platinum and cobalt, and also spent nuclear fuel and spent catalysts from industrial chemical processes. So how do we approach this problem of processing of these multi-metal waste substrates? Well, we could do it pyrometallurgically by melting, roasting, and smelting, but it's very much unsustainable. It's very energy intensive. It may not be the most safe working environment for the workers, and of course it's somewhat unselective. On the other side, we could do it solvometallurgically. By solvometallurgy, we could basically dissolve the metals. So what is applied now currently are, for example, traditional hydrometallurgical processes that include hard conditions, for example, very strong corrosive acids, very oxidative compounds, or even very toxic nasty compounds like cyanide, for example. We can also do hydrometallurgical chlorination with chlorine gas that was, for example, as you might know, used as a war gas, or even amalgamation in some parts of the world with very toxic liquid mercury. So those traditional hydrometallurgical approaches are not very sustainable, and of course they are also not very selective. So more or less all the metals dissolve in these very hard conditions. We can also apply more modern hydrometallurgical approaches. For example, urea leaching, thiosulfate leaching, iodine iodide leaching, or glycine leaching, and so on, can be applied as more sustainable approaches, as the chemicals are not so dangerous and they are more environmentally safe. Yet they are still somewhat not selective for the metals. So what we in our research group are trying to do is to essentially recycle these noble metals using organic media. Organic media can be sustainable, of course, if we use sustainable solvents, as I will show you in the following slides, like organic solvents like ethanol, ethyl acetate, and so on, and maybe ionic solvents, for example, dipiotectic solvents and liquid organic acids. Why organic solvents? The reason behind that is also that we can control the selectivity better, since we have many compounds that are soluble in organic solvents that would not be soluble in, for example, organic media. To give you an example for one metal, for example, gold. If we have a gold ore, or if we have a gold waste product, for example, gold fingers, as I will also show you later, but here you can see these are gold fingers from the computer motherboard. These are the connection fingers that are found in every computer and also in other appliances like mobile phones. So for example, if we have gold ore or gold waste material, we can dissolve gold, for example, using cyanide leaching by applying cyanide, which is very toxic and environmentally challenging. More safe, more sustainable approaches, for example, iodine iodide leaching, but iodine is quite expensive even compared to gold. You can check the prices online and you will be probably as surprised as I was. And then we have different approaches to dissolve them in organic media. For example, we could use stoichiometric amount of iodine, whereas in the iodine iodide leaching we need large amounts of iodine that, as I said, is very expensive. So we could also do it by stoichiometric amount of iodine by applying the correct ligands. So what we tried to design was that we would dissolve gold by using just a catalytic amount of iodine, and we would substitute this iodine in the reaction mixture with something cheaper and safer. So what we did was we designed this catalytic cycle where gold is first dissolved with elemental iodine to form this species 1 on the slide, so gold iodide, and then we chose this organic ligand that was only soluble in ethanol. Of course, this one is insoluble in water, so we could play with different organic ligands, as I said before, just because we have less polar media, organic media. So we choose this 2-mercaptobenzimidazole as a substituting ligand for iodine on the gold cation. So if you check the catalytic cycle, first one molecule of 2-mercaptobenzimidazole comes and substitutes the iodide on the gold plus centrum. Then the second molecule comes and forms this stable complex 3 that is dissolved in gold. And the expelled iodides can be reoxidized by hydrogen peroxide back to elemental iodine that can again start the catalytic cycle by dissolving more gold. If you check the table that is on the slide, you can see that if we include all, so stabilizing ligand, oxidant, and catalyst, we get 100% of the gold dissolution. But if we exclude one, we get some other percentages, and if we combine all of those percentages, we still not come to 100. So this was one of the first kind of proofs that cooperation between 2-mercaptobenzimidazole as a ligand, hydrogen peroxide as a terminal oxidant, and iodine as a catalyst exists. So we have also been tracking this reaction using flame atomic absorption spectrometry and ESI HRMS. As I showed you before, we saw that essentially the concentration of the species 3 that I showed you on the previous slide, let me remind you. So the concentration of the species 3, so the final gold product, is rising through the whole reaction procedure in these 24 hours that we were measuring. But the concentration of 1 and 2, you can check them now on the slide, their concentration are more or less stay somehow constant through the whole reaction. That also means that they are a part of the catalytic cycle, and the stabilized complex concentration is rising. We've been observing it for 24 hours. We saw that there is 3 different rates to this reaction, depending on the concentration of the, of course, iodine that is getting recycled in this process. And of course, whenever we are thinking of recycling the material, we have to think of first dissolution and then of precipitation of the metal back to its original elemental form. So how we did this was we used a reductant. In this case, we used sodium boron hydride. It might be that in the future we will try to find something more sustainable. But the sodium boron hydride was able to reduce these compounds that were forming because the ligand was decaying. Of course, we have the oxidative conditions, so the ligand is decaying. So this reductant was able to first recycle to some extent the ligand and then also precipitate gold itself. So our next study, and this was the first study of my postdoc here, included using sustainable ionic organic media to dissolve gold and copper and silver as 3 maybe most known noble metals. So we used deep eutectic solvents and liquid organic acids as ionic organic media. Deep eutectic solvents, as you might know, are kind of similar to ionic liquids, but are different in the way that they are produced by 2 partners. So one is ionic, containing cation and anion, and then 1 hydrogen bond donor that kind of takes away the anionic partner from the cationic partner and kind of loosens the crystal lattice, and which makes the whole thing liquid at room temperature. Of course, the procedure is that we kind of take 2 compounds, we heat them together, and then they are liquid at room temperature. And these are deep eutectic solvents. Why we chose to work with deep eutectic solvents and organic acids is because they are safe, they are affordable, they can be biomass derived, and they are potentially recyclable. So the potential recyclability of the media or of the more expensive components of the dissolution system is very important for sustainable development. And with these deep eutectic solvents, their vapor pressure is very low, and they have a very interesting solubility properties, which I will show you in the following slides. So they are potentially recyclable solvents. Since we are dealing with dissolution from the metal 0 to metal ions, deep eutectic solvents and organic acids they are made of ions, so they have high ionic strength, and because there's so many of the components that we can change, they have tunable structure. So they can supply media as well as also the ligands, so the anionic ligands for the dissolved metal cations. So we try to design this sequential selective dissolution of coinage metals in this recyclable ionic media. So what we were trying to do was we chose one of the more famous examples of deep eutectic solvents, which is choline chloride urea. So you can produce this deep eutectic solvent by using choline chloride and urea, and you get this very viscous liquid. And we were playing around also with lactic acid. What we managed to do was to, with using the proper oxidant, we were able to dissolve each metal separately from the other 2. So we had conditions with choline chloride urea using hydrogen peroxide as an oxidant, where we could dissolve copper, but we couldn't dissolve silver and gold. So we had the first selectivity. But if we switched from hydrogen peroxide to oxone, You can check the far right part of the table there. So choline chloride urea oxone system can dissolve both copper and gold. But if we already dissolved the copper before with hydrogen peroxide in this media, we could have already here a selectivity to dissolve gold. So then we only needed to find some conditions where we could actually dissolve silver. So we were playing around with lactic acid based diputactic solvents, and we found out that lactic acid itself using hydrogen peroxide can dissolve silver, but also copper. But then again, we also had a system from before that could dissolve copper alone. Therefore, the sequential selectivity is that we have one system where we dissolve one metal. So if I go through this table, so in choline chloride urea diputactic solvent, by using hydrogen peroxide, we can dissolve copper, whereas silver and gold are not soluble. Then we transfer this silver and gold with other parts of the waste to the next batch, and we dissolve selectively silver in lactic acid using hydrogen peroxide, where gold doesn't dissolve. And then for the last dissolution, we can dissolve gold using choline chloride urea oxone, and we can dissolve gold from other plastic and other waste materials. So as I said, we try to prove that these solvents are also recyclable. So what we did was we tried to close this recycling loop, so to get back the solid single metal compounds back. So if we go first through this copper coin, so as I said, copper dissolves in choline chloride urea with hydrogen peroxide, forming this copper 2+ ions dissolved in the diputactic solvent. And if we add the ethanol and ammonium carbonate, so ethanol here acts as so-called anti-solvent. So ethanol essentially precipitates more or less the copper species as this dicopper chloride trihydroxide, but dissolves the unreacted choline chloride urea diputactic solvent. So after separating the solid and the liquid on the scheme S and L, so when we separate those, we can recycle the diputactic solvent by drying it and getting this anti-solvent ethanol out. We can recycle it in 83%. So similarly for silver, silver is dissolved in lactic acid using hydrogen peroxide. So silver dissolves, of course, as silver 1. And then we can add, in this case, ethyl acetate, which precipitates silver lactate as a insoluble silver species, and the unreacted lactic acid dissolves in this ethyl acetate. And then we separate silver lactate to lactic acid in the ethyl acetate. After evaporating ethyl acetate and drying, so to get the water out, we can recycle this lactic acid back to its original form and reuse it again to dissolve more fresh silver, as in the case of copper. The gold was a bit more tricky, so gold dissolves in choline chloride urea oxone system, forming these gold 3+ ions, and then we had to unfortunately reduce it in situ inside of this diputactic solvent to get elemental gold back. The unreacted diputactic solvent was similarly to the copper system dissolved in ethanol, so after we separated the gold, elemental gold out, we could recycle this solvent. I could show you now this. For example, this is the diputactic solvent that contains copper. It's this nice blue color. This blue color is very much known for copper 2+. For example, this is the diputactic solvent that contains gold. As you can see, it's a very nice gold color. So how we knew immediately that this is gold 3 is because it has this very nice gold color. So gold 3 cations have this very nice, usually this very nice gold color, whereas gold plus is usually colorless. So as I said before, I can maybe even show you again this slide. So as I said before, after this copper is dissolved, we put there ethanol and ammonium carbonate, and we precipitate out this copper chloride hydroxide. You can again see that this is a very nice blue color, which is very much known thing for the copper 2+ ions. After reduction of this copper +1 salt, we can of course get this elemental copper. I don't know if you can see from here, it's this very fine black powder. Of course, how big the particles are really depends very much on the conditions that we were using, but somehow I hope I managed to show you that this process is very easy and to reproduce and to do. So of course we wanted to apply our systems to the real life waste. As I showed you before, this part of the computer motherboard that has this gold connection fingers. So first these gold connection fingers are actually very interesting waste material. So essentially they are comprised of gold that is printed on top of nickel, and then under nickel there is a layer of copper, and then of course this ceramic plastic composite that forms these motherboards from the computers and cell phones. So what we wanted to do was to separate copper and gold from these gold fingers. So first we used some organic solvents just to get rid of the plastics coatings and silicones and polybrominated fire retardants, and then we used HCl aqueous to dissolve base metals like aluminum, tin, zinc and nickel. Of course, then we could apply our choline chloride urea system that selectively dissolves copper, and we dissolved copper and closed the recycling loop as I showed you in the previous slide to get back elemental copper. After that, we could apply, because there was no silver in our samples, so we could directly apply this system to dissolve gold in this choline chloride urea oxone system as I showed you before, and we got out, by closing the recycling loop, the elemental gold. So how these materials look before and after, you can see these are some parts of the computer motherboard. You can see very shiny layer of this copper, and after the dissolution there is no more copper left. There is only this plastic composite there. And for the gold fingers, you can see very nice shiny gold fingers before the dissolution, shining of real elemental gold, and after the dissolution all the metals disappear. There might be a little bit of nickel left, which was very much beneficial thing for us. As there was no silver in our computer waste, we still wanted to try to get silver out of something. So what was the best substrate to extract the silver from were solar panels. So solar panels, especially the more expensive ones, the ones that we have on the roofs, the ones that are, for example, in the Alepa bikes station. So these solar panels are made of silver electrodes. So how is the solar panel comprised? So it has this. So this is one part of this solar panel that I bought on Tori, and then I destroyed it in the parking lot with my boss, and then of course we cut them into small pieces and we got rid of this glass first. So essentially how the solar panel is made, it has this protective layer behind, it has this glass layer in front. So after this glass layer, as you can also see from these pictures, after this glass layer there are very small shiny stripes that are actually a silver electrode, and what you don't see is between this silver electrode there is a ceramic layer, and then below this ceramic layer there is an aluminum electrode. So essentially it's glass, silver, ceramic, aluminum, and then whatever motherboard, plastic, and so on. So what we were trying to do first is we were trying to get rid of this protective plastic by using organic solvents. So this is how we got rid of this glass and the motherboard. And then we unfortunately, in this case, had to do it manually to get the glass away from this silver electrode. In industry, if this process would maybe stick, then of course they would probably grind the whole thing using some big mechanical grinder and then extract silver afterwards. So we got this exposed layer of silver, and then of course we first needed to get rid of the aluminum electrode that I was telling you about. We were using aqueous acid, and we just got rid of this aluminum and parts of nickel, and then we could apply our lactic acid hydrogen peroxide system to get the silver out. Unfortunately, the concentrations in our system were so low that we needed to precipitate it, and the best way to precipitate small concentrations of silver is to just introduce the chloride, and then you get out the silver. Chloride is very insoluble compound. So of course our system can be applied on all three metals together. So as I showed you before, this part of computer motherboard with copper grid is there on the left side, then the silver wire and the gold fingers. So first we apply our first system that is selective for copper, and as you can see from the copper grid, there is no more copper on the grid. What happens besides that is also that the copper below the gold connection fingers is dissolved, so the gold connection fingers essentially fall off, but they do not dissolve, so they were left in our reaction vessel that you can see on the right side of the slide. Then we could apply our system to dissolve silver using lactic acid hydrogen peroxide, and still gold doesn't dissolve, as the method was designed for this. And at the end we could apply our dissolution system for gold to dissolve gold flakes from this reaction mixture, leaving just this ceramic, plastic, and their composites from the motherboards. So I hope I've been able to show you that maybe the organic solvents could be the next generation of solvents to process these metals. I would like to thank all the collaborators on these two projects that I showed you today, and I would like to thank you for attention at this Gadolin Science Thursday. Now I guess it's time for the questions, and you can type them in the system on the Gadolin website. So I see some questions here, so I might just read them. Very interesting research, thank you. I wonder how much do your research group collaborate with chemical industry companies for a science and from funding perspective. So after we published this last work, different companies contacted us. They were not all, how do you say, very sincere with this, but some were trying to kind of collaborate with us to maybe even apply some European funds with them. So we are collaborating currently with some companies on metal trapping, and we will further collaborate under this REMHub project that was recently awarded to us for the recycling of permanent magnets. So mostly in this case lanthanoid chemistry of neodymium and samarium and dysprosium. And we, in this consortium, there's a lot of partners that would collaborate with us. But as I said, we got contacted by some companies. Some were very interesting. One solar panel company from Slovenia contacted me, but there were also some companies that were a bit more, should I say, suspicious, and they just maybe wanted to get some profit on expenses of some people. Okay, Amy said, very interesting indeed. Why is it important to recycle the solvents as well? So when you have a solvent that is, so essentially from the economic point of view, it's cheaper to buy some strong acid. But of course the strong acid is not very sustainable. The strong acid is dangerous for the workers, and the strong acid cannot be recycled. But it's cheaper maybe than the dipytectic solvent when you start your process. So because dipytectic solvents, the initial cost is a bit higher than for the acid, then we can somehow fight this by recycling them. And if they are somehow more economical, then the system takes it. Of course, we have to be aware of the price in this case. So the recycling is economical, but of course it's also even very much sustainable if you can just recycle and reuse it as many times as you can the solvent. I hope I answered you. In this chemical, so the next question from Elite. In any chemical process, solvents usually represent by far the largest fraction of the chemicals used. If they are not recycled, they represent the bulk of the chemical waste. Yes, so this was somehow what I tried to do, but this might be even better. So Alexandra said, extremely interesting, Dr. Zupanc is truly an expert on the field. Thank you, Alexandra. So Carolina, thank you for a presentation. What are the main challenges in recycling metals from electronics and batteries, and how can new methods help to overcome these difficulties? So the main challenges, I think, are, since we're trying to be a part of a sustainable development, and try to lower our carbon footprints and try to pollute less, I think the main challenge is to be more sustainable. So to use more sustainable chemicals. So more green solvents, and then cheap, non-toxic ligands or compounds that can dissolve or help to dissolve or keep the metals dissolved. Of course, we have to consider also all other chemicals, right? Like reductants to get the chemicals back. Even if we use electricity for reduction, this energy has to come from somewhere. So there is no free energy, there is no we have to sacrifice some chemicals to get some others. So the whole energy consumption is here very much connected with material consumption. So I guess sustainability is one of the most important things and challenges in the recycling sector. And as I said, selectivity, because selectivity translates into sustainability. If we could design the method that would just take out metals one by one, so one metal, one method, this would be, of course, perfect. So sustainability and selectivity. I guess if there's no more questions, And I would like to thank you again for participating in this Gadolin Science Thursday. So thank you for your attention, and you're welcome to join next time.